Alright, we're going to learn quickly about the principle of inclusion-exclusion. We'll get started off with an example here. But before we start, I should say that the basic idea to the principle of inclusion-exclusion is that in order to know how many elements are in the union of some number of sets, you actually end up needing to know how many elements are in all of the intersections of all of those sets. So here's what I mean. So let's say we have 60 people in a ballroom, and there are drinks or something being served, or snacks or something like that, and 27 people there are coffee drinkers, and 29 people there are soda drinkers, and 20 people there are tea drinkers, and we want to know how many people there aren't drinking coffee or soda or tea. Well, it turns out that it's not enough just to know these numbers. We also need to know the number of people who are both tea and coffee drinkers. And we also need to know the number of people who are both tea and soda drinkers, and the number of people who are both coffee and soda drinkers. And then we also need to know the number of people who are tea, coffee, and soda drinkers. That is, who will drink all three, who are fine with all three. And when we do that, we can find out the number of people who don't drink any of them by adding up all of these numbers inside the Venn diagram and subtracting it from 60, and that gives us 12. So this is nice, and it's easy to look at and sort of intuitively understand, but it's a little crowded, especially suppose that there were a fourth category here, like green tea drinkers or something. It would be difficult to draw in another bubble, and so it would be nice if we had a method for doing the same sort of thing that didn't rely on our ability to draw nice looking Venn diagrams, and that's where the set theoretic approach comes in. So let's say that we have two sets, A and B, and they're subsets of some set X. How many elements are in neither A nor B? That's kind of what we did up here, but now there are only two categories instead of three. So I'll just sort of present it and then explain it here. Well, it seems pretty straightforward that if we want to know how many elements are in neither A nor B, this is just the cardinality of X, the set that contains them, minus the cardinality of the union of A and B. And you recall that the union of two sets is the set of all elements that are in either A or in B. But how do we tell what this union is? And that's where the principle of inclusion-exclusion starts to come in. We need to know how many elements are in their intersection. So it seems like we should just be able to, if we want to know how many elements are in the union of two sets, that we can just add the cardinalities of those two sets together. And we can in the case where the two sets don't share any elements in common. For instance, if A is 1, 2, 3, say, and B is 4, 5, 6, well, those two sets don't have anything in common, and so their union is 1, 2, 3, 4, 5, 6, and so the cardinality of that is 6, which is the cardinalities of the two separate sets just added together. 1, 2, 3 plus 4, 5, 6. That's 3 and 3 is 6. However, if A and B happen to contain some element in common, so let's say that they contain X in common. So when we are calculating this sum, we're adding everything in X, or everything in A, and that includes X. And then we're adding the number of elements in B, and that also includes X. So we counted X here, and we counted X here, which means that we've now counted X twice. But X should really only count for 1, because it's just one element in this union. So we need to subtract by everything that we counted twice. So X is in the intersection of A and B, that is, it was in both A and it was in B. So we need to subtract it because we accidentally counted it twice here, and that's the principle of inclusion-exclusion for two sets. And so to finish up our question up here, how many are in neither? Well, it's just the cardinality of X minus the quantity of the cardinality of A plus that of B minus the cardinality of A intersect B. Now for three sets, it's really quite similar, but I'll just run through it more quickly. So, okay, the cardinality of A union B union C, right? So again, we start out just by kind of dumbly adding up the cardinalities of the individual sets, but now we know that we've overcounted by everything that's in the intersections. So we have to now subtract everything that's in the intersection of A and B, and then subtract that everything that's in the intersection of A and C, and then subtract everything that's in the intersection of B and C, because we counted all of those elements more than once. For instance, if x is in, well, it's just the same argument as up here. So now we're almost done, but we're not quite done, because let's suppose that x now is an element that's in all three sets. So what did we do? Where are we standing with x? So we counted x here once, and we counted x here twice, and we counted x here 3 times. So now we've counted x 3 times. That's twice more than we should have, because x should only count for 1, because it's just one element. So we then subtracted it here, though, because it's in all 3, so that means it's in A and B. And then we subtracted it again, because it's in A and C, it's in all 3. And then we subtracted it again, because it's in both B and C, because it's in all 3. So instead of having 1, we've now subtracted it down to 0, because it was 1, 2, 3 up, and then 1 down, 2 down, 3 down. So now it's at 0 again, when it should really be at 1. So we now have to compensate again. And we do this by adding everything that we accidentally subtracted too much of, and that's everything that's in the intersection of all 3 sets. And we can see that this pattern is arising, and we could do the same thing for 4 sets. But I'm running short on time, so I'll just get to the next example here. Here's a little application of this involving voter satisfaction. So let's say that there are 2 candidates, A and B, and we poll a bunch of people, and 50% of those people say that they'll be satisfied if A is elected, 45% of those people say that they'll be satisfied if B is elected, and 25% say that they'll be satisfied with either one. So what can we learn from this poll? Well, if we pretend that there were only 100 people, then this is the same thing as saying that 50 were for A, and 45 were for B, and 25 were for either A or B. So if we want to know how many people are counted here, how many people are in the union, how many people will be satisfied, then we have to, it's just the same thing here as this case, as this case up here, where we're taking the cardinality of the union. So in this case, the cardinality of the union of A and B represents the total number of people out of 100 that will be satisfied at the end of the election. So in this case, it's 50% plus 45% minus 25% is 70%. So what that really means is that 30% of the people won't be satisfied no matter what happens. And so that's something to keep in mind when you're thinking about elections and polls. All right, thanks.